Hello, this is the fifth video of a fourth calculus series on integration techniques for OCR Pure Core Further Mathematics, and we look at integrals using either x equals a sin u or x equals a tan u as substitutions. In previous videos we have already seen that we can use for substitutions x equals sin u and expressions involving the square root of 1 minus x squared, and x equals tan u and expressions involving 1 plus x squared. These substitutions can now be extended to x equals a sin u for expressions with the square root of a squared minus x squared, or x equals a tan u for expressions with a squared plus x squared. In this example, we'll notice that the integral is of the form square root of a squared minus x squared, where a equals 5. Therefore, we'll choose to use x equals 5 sin u as a substitution. We will have that dx by du equals 5 cos u. We also need to think about our limits. When x equals 0, u will also be 0. When x equals 5 over 2, in other words sin u equals a half, then u will equal pi by 6. So now we're ready to substitute into our integral. We know that our new limits are 0 and pi by 6. And under that square root we now have 25 minus 25 sine squared u. And then we are multiplying by 5 cos u du. We know we can replace the 1 minus sine squared u and take out that factor of 5. So let's take out the factor of 5 first of all. And then we'll replace what's under the square root by cos u. And then we can see that we've got another factor of 5, so that would make 25 taken out, and another cos u, giving us cos squared u du as the integrand. We can't integrate cos squared u easily, so we will use the double angle formula. And this will give us 25 over 2 with cos 2u plus 1 du. So we've got to this point here on the previous slide. We can now easily integrate cos 2u to being half of sine 2u plus u. And when we put those limits in, 25 over 4, root 3 over 2 plus pi by 3. Note that it's really important to know when the limits are x equals and u equals, as that is where common errors often occur. In this example, we're asked to show that the integral can be rewritten as a third of cos u being integrated with respect to u, and to hence solve that integral. We notice that this is of the form a squared plus x squared. But we also need the coefficient of x squared to be 1. Start by rewriting 1 plus 9x squared as 9 1/9 plus x squared. Then I can see that a squared is 1/9, and so a will be a third. And I'm going to use x equal to a third tan u. This will give me dx by du as being 1/3 sec squared u. So starting with that integral at the top, I can replace this by 1 over 9 to the 3 over 2, 1/9 plus x squared to the 3 over 2 dx. And then using that substitution, that will give me 1 over 27. On the top it will be 1/3 sec squared u du. And the denominator will be 1/9 plus 1/9 tan squared u, again to that power 3 over 2. That bracket will be 1/9 sec squared u to the power 3 over 2, which would give us 1 over 27 sec cubed u. We can see here that we're going to be able to cancel down quite a bit. The 1 over 27s will go. We can take out that factor of a third outside the integral. And the sec squared, the numerator, will cancel with the sec cubed denominator, leaving us 1 over sec u du, which, given sec and cos functions are reciprocals, takes us to the desired 1/3 cos u du. So during that process you can see that you need to be really careful with the fractions and the powers. We now have an integral that we can easily integrate, and this will be 1/3 of sine u plus c. So all we have to do now is translate that back into using x. Well, we knew that x was 1/3 of tan u, and we also know that tan u will be sine u over cos u. Cos u will be 1 over sec x, which is also 1 over the square root of 1 plus 9x squared, using this reciprocal and also the identity that sec squared x equals 1 plus tan squared x. Thus we can write that sine u is going to be 3x over the square root of 1 plus 9x squared. So, cancelling down those 3's, we get a final answer of x over square root of 1 plus 9x squared plus c. You have to be really careful with the numbers. Because the x equaled 1/3 of tan u, then 3x will equal tan u. And then we use this identity, giving us this, which might not be immediately obvious from the initial substitution. Alright then, in general we can use these substitutions, x equals a sine u, where we have expressions with the square root of a squared minus x squared, and x equals a tan u, where we've got an a squared plus x squared. Note that the resulting integral may need further techniques to be applied to the use of double angle formula or identities such as tan x equals sine x over cos x, and remembering that cos and sec are reciprocals. Transforming back to the original variable, usually x, may take some care. And do remember that definite integrals need to have the limits transformed to the equivalent values for the new variable that you're using in the substitution. This is the last video of the Calculus 4 series.